My name is Moody Hadi. I work for Standard & Poor's Market Intelligence. I had new product development for credit analytics. I'll explain that a bit later after going through this. So today we're going to show a few applications of natural language processing, specifically for financial, basically, services. Generally, as everybody here knows, machine learning has been, over the past decade or so, it's been very popular. It's been actively used in financial services, and we're a financial and data analytics company, and we have a few applications that differentiate our product line that will kind of gradiate the story through. So I'll first start with basically an overview of who S&P Global is. It's quite a big company, and then I'll go through a bit of the journey to get to the case studies. So there's a little bit of level setting. I've condensed quite a few presentations in the past into to this deck. So I'll kind of go through some of the basics and then get into the examples and the architecture within two applications we've developed. So S&P Global is several business lines, and three of the major ones is the ratings agency, which basically rates their privy to material non-public information. We've seen uppercase ratings, AAA, BBB, that's the ratings agency. There's the index, which is S&P 500, the Dow Jones. You see that the stock tickers, so that's a different business line. And there's S&P Global Market Intelligence, which is my business line, which is really a data analytics provider. So in my business line, what I really focus on is credit, market risk, and operational risk. And me specifically, as head of new products, I'm trying to create differentiation using a lot of unstructured data and machine learning to basically to compete with other data analytics providers. Okay. Oh, yep. So we'll go over like some techniques of generally machine learning and what that process of building application like that is, and then we'll go into NLP specifically, and then we'll go through two examples that relate to the above. So as a data scientist, typically you're going to get a business problem that needs to be solved. The business user is typically asking you to figure out what the algorithm is, and you can actually try multiple different techniques. I think someone earlier today was talking about complexity and the balance of that. Really, that's where your expertise comes in. But at the end of the day, you also have to kind of be able to explain back to the user why you chose one approach versus another, and if you tested different approaches. So that's a very important theme you'll see as we go through here. So just to kind of give you an idea, a lot of the process for basically building machine learning applications goes through basically these four major steps. The bad news is a lot of the time is spent really on data preparation. So, just recently we've had like basically gigabytes of data. We're working with some very unstructured things that we had to join together, and actually understanding the data dictionary, what those columns mean, what those features mean, and then joining them together in a way that doesn't confuse the information is quite time consuming. So really, I would say most of the time is spent there, trying to get to understand exactly what it is we're putting into the model. Once we have that, then we try different models, right? So you have to define, you wouldn't jump and basically try, random forest just immediately. You basically would try different techniques, ensembles, lasso, generalized linear regressions, they're not bad, logistical regressions, just to compare and define what orthogonal variables you want to include in your model, right? We run a lot of pairwise correlations, things like that, that reduce basically the number of features we have to handle. Once you've kind of settled on a few of them, right, you start training them, and you start comparing how the marginal benefit across the two or across the three or four is actually how it's behaving, because sometimes the lift isn't actually enough to justify basically going into more complex approaches, right? So again, once you settle on basically a happy medium, you've kind of explained that to the business users, you'll basically end up productionalizing it these days, using EC2 or Docker containers or Kubernetes, and running it in production and monitoring actively how the model is drifting against other basically other competing challenger models, so you can recalibrate if needed, right? So that's really the final step, which is, cheers, everybody's happy, yeah. So like one of the very common themes that exists is really figuring out the variance by trade-off. That's very common. It's a different transformation of overfitting and underfitting, right? So, bias is really trying to capture the fidelity in the underlying pattern, and variance is how sensitive is your model to very small perturbations in the data. And I have a little shiny app. You guys can play with it. You can generate your own moment generating process, data generating process, and then basically try different models and see how they behave. Here, like obviously you can see how the random forest is actually very sensitive to small perturbations in the data set that swings, right? And the quadratic regression is almost completely insensitive to it. And of course, because this is a dummy example, I cheated, and you can fit a nonlinear regression to it, and it works. It captures relatively the low bias, low variance that you actually want. Now, in the real world, these type of things don't usually occur that way. Sorry. So, yeah, in the real world, you don't really find these kind of really simple situations where you have the luxury of knowing what the data process looks like and fitting basically a series of different algorithms to it and getting like a low bias, low variance situation. So it's really very important to be able to explain the different basically trade-offs between what you're actually producing as a technique and in simple words to the business user why you chose one against the other and why, or sometimes they can make the choice too, right? So one simple way we've actually kind of had we've had basic success with is a simple grid like this, where in this case, just the same kind of similar situation we had before. You're looking at traditional techniques, generalized linear regressions. They're tightly coupled to the data. They require a lot of recalibration, but they need supervision, but they're very low complexity. When you actually show it to a business user, they can understand what's going on. They know the sensitivities to independent variables directly, right? So there is something to say for that, right? You look at random forest. They're not as tightly coupled to the data. They can actually adapt, right? They require relatively low supervision, compared to the above. And the complexities, these days is probably, I would say, medium, right? And then you go into some other techniques like gradient boosting and some more complex ones. And, they're low supervision, they're very, very highly complex to actually explain when you get a client call and say, oh, I don't understand what this number means. Why did this happen? It's very hard to explain it, and there are techniques now that help, but it's not quite as easy as the first one, right? So you want to basically keep that in mind as you're choosing different basically techniques and really presenting things like that, and you can change technique to basically whatever, like sometimes vendors, sometimes different combinations, ensembles of models, you can really change that into different basically options, right? And then really those two are critical. And it goes back to the whole overfitting, underfitting kind of situation and then the complexity, right? So, what? Oh yeah, maybe it's that. Oh, perfect, okay. All right, so now to go into natural language processing, like specifically here, basically this is how the pipeline looks like for an NLP, right? So really you've got, you're generally going to start with some form of text data. Now, whether it's machine readable or machine unreadable, you're going to have to solve that first. Once you have basically machine readable text, we'll go start with basically the left branch. You're going to have to tokenize, right, and do some form of sentence detection. And then you can basically use a bag of words, which is basically a simple dictionary approach with some weights against it. And in some cases, you sum the positives and subtract negatives, divide by something, right? Very deterministic, simple to explain. Again, it goes back to that low complexity. But it doesn't really capture a lot of the information in the text. Another approach, which is basically on the fourth basically area, you're looking at regularized bag of words. So how do you adjust the weights to the context that you're basically applying? And here you can basically use lassos or different basically ways to readjust the weights. For example, in my case, sometimes in public disclosures versus private disclosures, how to really capture that information and those topics. It works, but again, you go back to having to supervise it, basically, recalibrate, improve the dictionary, adjust the weights, but it's really easy to explain. The last option, which is the most popular one in the NLP world, and I have an example of this here, is actually using like basically machine learning, right? Using basic convolutions or LSTM, right? Now, one thing to keep in mind, you're going to have to create some form of annotations. Like most of the time, you're rarely going, at least in financial services, you're not going to find something out of the box that's pre-trained, or you can easily do transfer learning against. So what that means is you're going to have people actually looking at the text and actually doing context against it, all right? Once you solve that problem, then you go into the fun part, which is basically deciding and training the model, and then once you've trained it, you can effectively run through the same process here and get polarities and work with it. So anyway, that's just a kind of an overview of this thing. Okay, here we go. Okay. Yeah. Yeah, here we go, sorry. So again, to go back to the same matrix, right, which we've used basically for the second case study or first case study. Same approach. I think I kind of walked through most of it here, but again, keep in mind, I mean, we use basically a lot of regularized bag of words. My example here is actually convolutions, but it's very specific to actually Chinese documents, right? So we don't always end up using basically neural networks for everything, right? So same thing, and that really explains to the business user why you're taking one approach versus the other, right? So now let's go into the fun part. So basically, this is a case study on sentiment analysis for, in this case, Chinese public disclosures. So, one common theme at S&P Global, we have a lot of unstructured data. We actually buy a lot of data, we mine it, and we basically resell the output, the signals to clients. And we create our own data. So in this case, we basically identified public disclosures from a lot of Chinese companies, and we wanted to kind of create signals for both the mainland and for the US and European markets when there is a potential change in when they've announced basically something material to their financial health or to their basically business operations. And since these are public domain disclosures, you don't have any IP issues or data has to reside in China, so you can basically effectively mine it. And you have to keep in mind the size of the company, right? So, but typically they're listed. There's a few private companies in there that actually have to go through the regulation, right? So how would you basically solve this problem? I mean, in a very, very high level, you would basically take the PDFs. By the way, most of them are PDFs, so you're going to have to solve to convert unreadable text to machine readable text. We've used Tesseract and ImageMagick. We'll go over it a little bit, but to actually rotate and adjust those basically qualities. And then once you basically solve that, then you basically run it through the sort of structured data format to detect, in some cases, tables, in some cases to remove tables, and then really figure out what sections you want to actually operate with. So to go back, the first really biggest problem after the OCR stuff is how do you create labels? Because there's no such thing as basically public disclosure Chinese labels. So we built a Shiny app, and we actually hired financial Chinese native language speakers. And we basically gave them the documents, and in fact, we took the documents, sectioned them out into chapters, because some of them have actually relations to each other. And then we had them annotate individually sentences and paragraphs into the app, and then they would save it, and then we basically built our annotation set, right? So something unique, nobody, at least for the Chinese market, it's something quite unique that we basically were able to do. Now we've got a training set to actually leverage. So once you have that, you're basically going to end up with something like this. You're taking the document, you chapter it out. How do you define the chapters? Typically with the large documents, there are a form of table of contents with logical basically groupings and areas that you can basically figure out where they should be chaptered out. And once you know that, we run them through a classifier that basically says, hey, is this section relevant? Does it have something against my context given what I know from the annotation or not? And if it doesn't, I chuck it out. If it does, then it goes through the polarity calculator, which is actually going to basically read that basically section and figure out what the polarity is based on, again, what we had trained against. So not everything goes in. So like the bad news is you might start with 2 million documents, but at the end of the day, the ones that are relevant are, and I'm making this number up, like 200,000, But there is a reason for it, because most of the other ones are just a name change disclosure, or some, not even a management change, something very, very simple that basically happened that shouldn't go into it, you know? Yeah, so basically this is the underlying pipeline or architecture, right? So, I mean, I kind of touched on it a bit, but I guess I could highlight a few areas. I mean, common theme across both of these machine learning problems is the optical character recognition engine. I think the John Snow Labs, David basically was talking about improving the OCR. I can definitely relate to that. We use Tesseract. Other places use Textract. They're all bad, you know, so you're going to run into having to figure out in some cases, and usually they're the, you know, sometimes there's the things that go to the client that why is some text that seems to be simple hasn't been translated to machine readable easily. So that we've kind of handled a lot of that through the pre-processing piece. So we do some corrections automatically to kind of augment when we can detect like something was one character or a few were mischaracterized. And a lot of it is also typically related to the image, to document quality. So a lot of it is actually trying to re-rotate the document, trying different sharpening contrast ratios to get it to the point that basically the OCR engine can actually read it. So that's really the first building block. The second one is basically sentence and it's a little more specific to Chinese or simplified Chinese, is basically sentence detection. Where do you actually stop? Right, and what actually grouping of characters are related to each other. So what we've done is actually we created we vectorized it, which is the next bullet, but that's how the pipeline. But we've actually said, hey, you know what? Let's basically try to kind of. We looked at fast text from Facebook at the time, and we created our own vectorization algorithm to see when I send it a word, can it figure out what the analogous terms are in order in financial context. You know, so obviously positive, for example, in healthcare means something different than positive in finance, right? So those kind of subtleties are important to put into the vectorization, which also requires, by the way, annotation, right? So once you have that, then you can actually use that because there's a series of basically matrices that you can run your convolution and neural network against. The last box at the bottom really is just highlighting like basically the training algorithm. Like you're going to have to do a lot of hyperparameter tuning and to go back to the original bias variance, like am I overfitting or am I underfitting? A lot of that, like tweaking the dropout layers to avoid that, trying different techniques. But once you settle on one, you basically run it effectively. It can be deployed in scale elastically across basically a lot of nodes, and you can process any document. And then the last little one here is sentiment attribution, which at the time was kind of more cutting edge. Now it's getting a little less cutting edge, but we had a lot of success using model agnostic explanations, LIME. Very simple way of looking at the world, but very powerful because you kind of really can take out individual features and see how much they've impacted the polarity. And something simple like that, although computationally expensive, goes a long way when you're actually publishing basically, you know, a continuous series of basically probabilistic estimates of what the context of a document is. Like something very complicated, you say, oh, well, look, if you take out this paragraph, it really has a big impact on the swing. It's like, oh, I see now why this is negative news, you know? So again, the downside of it is computationally expensive. So, but I think there are probably similar techniques that can run on GPUs. Maybe the NVIDIA guy has something, but like there are other techniques maybe that can actually do the same thing in a more computationally efficient manner, right? Yeah, so once you've built all this, the fun part is how do you explain it to people, right? Like, because it's like, you know, you show them basically an ROC curve, an AUC curve, and like, you know, all this fun stuff. It's not really going to kind of move the needle one way or another. So what we've done, we've actually built a Shiny app with simple clickable, and you can do it in Dash as well now. Like, you can simple click through buttons to actually highlight exactly what I explained. So you can click on a particular document over a time series. It fits basically what, you know, usually people in finance like smooth, continuous things, right? So something that's already smooth, but if they want to look at the underlying data, they can click on it, and it takes them specifically to that section and that area, and it emulates, and this is through LIME, it emulates effectively what kind of a bag of words does, especially when you use a bag of words and look at density of basically words together. But I think it captures a lot more of the nonlinearities in the text than basically than bag of words. So, and then that's cool because then the business users can really use this and play around with it. They can kick the tires, so to speak, and see what's going on. And then the other advantage is you can create basically that like lower quadrant here, the third lower quadrant. Like you basically can create a storyboard. So you can click on a company and actually figure out, if you didn't know who it is, especially when you're managing surveillance and you're managing risk, what actually, your boss asks you, hey, what happened to this X, Y, and Z company? Like, well, I don't know who X, Y, and Z is. You can click on it and you quickly condense the relevant information over a period of time in a very simple storyboard that you can push out as a tear sheet. Yeah, which kind of helps a lot of people. Yeah. So, again, so out of sample testing, these are companies that weren't in the sample set, but they had material changes. This is like the ultimate test, right? You know these companies, it's like Evergrande, if I run it through this, basically. Like, these companies had material issues. If we run the text against them, do we actually get a negative, basically, response? And yeah, we do, right? And in fact, the interesting thing that you notice, the pattern is typically like a large negative swing and a positive, and that's usually because either like a state-owned entity or some related entities have basically effectively bailed them out. So they had basically a technical default, but they got restructured. So the difference between restructuring and default in that region is very slim. So that's that pattern that you see repeating it all the time, is basically there was technically a default and then basically a bailout. So this is basically the natural, like a real NLP sort of approaches, right? In a pretty specific area, but I think that's where neural networks actually really plays a big role, right? Because the context is very well defined, the language is difficult, arguably, some of the Latin-based ones, you could probably get away with some of the regularized bag of words, The next one is more interesting, and it's more typical to, I would say, traditional finance, right? So here, basically, in risk management and in financial services, there's a term called spreading, and spreading really literally means taking financial statement line items, and unfortunately, for a long time, looking at the document whether on paper or on a screen and typing it in line by line in order to effectively run into your internal models. And the reality is a lot of banks, a lot of large non-financial corporates actually do that even today. In the public company universe, this is less of an issue because companies like S&P, we collect that data, they have to disclose it, and you're there. In the private company universe, this is a big problem, right? Because you don't normally collect that data anywhere. It's not available, right? So in Europe, there's more paths, but in the US, for sure, it's not. So the counterparty actually has that document, and they have that information. So what you want to do is basically emulate what you have in the public company universe, right? You're sitting here with this large ton of weird scanned paper, and you want to get to that because that's basically where you're going to make a decision. Oh, yeah, perfect. So what you do is, again, similar commonalities to the other one, right? You're basically still going to, unfortunately, deal with the OCR. You're still going to do image enhancement. And here you can almost ignore the text. You really just care about tables because financial information is typically presented in tables. You create the structured metadata output. The difference here is there's a human in the loop, right? So there's an algorithmic assignment here, which, by the way, this does use a dictionary-based approach. No way around that in here. There is, but it's not. Anyway, but you use a dictionary approach. Now, what you want to do is have the user augment or kind of train it in real time as they see things that were off, right? So what you can do is using the interface, you can have them, like we do, is thumbs up, thumbs down, and they simply validate very quickly the stuff that wasn't assigned or was assigned or was misassigned, and if they assign it themselves, it goes back into our dictionary for that specific company. We don't share dictionaries across companies. And that really improves the accuracy. So it does require, there's no secret sauce. The human in the loop is required. You're just trying to reduce the time that they're working on. Some solutions out there, they look at the public company universe, very defined. Like you look at S&P Global's financial statement the last probably 5 years, it's been exactly templatized. You can run templatized parsing, you don't really need. But again, in the private company universe, woo, like it's basically whatever fits the person at the point in time, you know? So, you know, be very careful there, right? So yeah, I'm not gonna bore you too much, but I'll just hit on a few areas. But like, I mean, again, similar themes, like this is how the pipeline really looks like, right? You're looking at, you know, extraction, table detection, structuring the metadata output, running through the assignment engine, which in this case, by the way, this is mostly Latin-based or Latin script-based and Slavic. But basically, the fuzzy joins on the strings, there are different algorithms to actually look at semantic distances, and you will have to try multiple different ones in order to reside on the one that has the closest one. And then again, same process runs through the scoring engine, save it, and then as a prototype, in this case we use Shiny, you could use Dash, and basically once you know what it is, you build the JavaScript-based like web application, right? I'm gonna skip through this. Again, we're using like basically highly elastic computing. Here, one thing to keep in mind, a lot of the documents and the OCR is computationally intensive, so the routing algorithm to different queues is quite important, even with horizontal scaling, right? So we had to write some different algorithms to basically manage the experience as people are hitting on the uploading more and more dense documents. So some of these documents can be like 200 pages plus, right? And the majority are smaller typically, but you don't want the 200 page to take over your whole EC2 basically instance and then you're done. So you will want to basically do some pre-calculation and routing before you kind of use basically the out-of-the-box AWS elastic scaling, right? Again, this is basically the preliminary. This was the app after that's the prototype app. This is in production already. Looks similar but cooler. But this kind of got us through the client advisory board and a lot of explanations. And you can see here and there where the thumbs up, thumbs down is. So, in conclusion, I mean, try it out. These are all production applications. Honestly, you can probably, the emails will probably come back to me, but you can, feel free, read about it a bit. If you're interested in looking at it, send it over. These are the URLs. Future extensions, I mean, again, I think I touched on them. I mean, we're not using bidirectional encoding yet. We're not using Elmo yet. But I honestly, we didn't really see much of a boost in this case. I think some of the other ones are TBD, basically. It's worth a look. And then really trying to figure out transfer learning is very interesting. I mean, that's a common thing, but we haven't been able to use it as much in this case, but yeah. And then, I think I hit on the model agnostic explanations. Hopefully, that's the paper. It's very helpful. And I ran out a little bit, but to tease my collaborators, I put their pictures here. So if you see them around, you know what work they've done. And that's it. And if you have any questions, please, I think we have a few minutes. I'm sorry, like 3 or 5 minutes to go over questions. So, yep, thank you.
So this might not pertain too much to the financial space, but how do you handle sarcasm?
Sarcasm.
Yeah.
It does. It's not here, but you're right. I don't know. Like we do have earnings calls based ones where you could probably look at that, but I would think you would look at the attenuations of how a person speaks and then use that as a part of your annotation. I don't know how, we have a company called Kensho and they do the speech transcripts. So, yeah, and financial documents, hopefully not, right? Yeah.
Hi, how are you?
Good, how are you?
So I'm sure you're familiar with the LIBOR transition, right?
Yeah.
Yeah. My colleague and I worked on a few of those projects.
Oh, awesome.
And one of our biggest challenges was table. So I saw you mentioned table detection and handwritten dates. So curious to hear your experience in that, if you could elaborate on those 2 points.
Yeah, sure. I mean, yeah, no worries. The table detection algorithms, they're rule-based, right? So a lot of it is trying to create a series of rules on what documents you are looking at. So I don't know what your input is, but a lot of it we've really looking at how far the borders are from each other. Like number one, if they're borders or not, and if number two, if they're not, is there density basically between the words and the numbers, and then you can kind of detect it. But there are a lot of like different table, like for something like a LIBOR transition, you're probably getting a table anyway. That probably was generated in Excel, so you might want to look at it the other way, like meaning use Excel, But yeah, and on the fixed income side, yeah, I think that's taking longer than we'd like, right? So, yeah. I'm sorry. Handwritten dates, yeah, that's I don't deal with the I know what you mean. Yeah, like with the OCR is the major issue there, right? So. Yeah, like a lot of these are pre-typed and re-scanned. Yeah, it would require like I think a lot of. I mean, my experience with Tesseract, it didn't really do too well when it's scripted, like when it's joined. I don't know. Sorry.
First of all, fantastic presentation. That was incredibly insightful. 2 quick questions. The humans in the loop process for extracting the tabular data and fixing it, was that internal software that you guys developed, or was that an off-the-shelf tool?
No, we developed. So like detecting the tables themselves, we developed it because we knew the corpus, we had the data, and that was kind of funny enough. It was related to the first project. So the first project we had to exclude tables because we didn't want to bias it on finance. We wanted to basically on financial numbers. We wanted to only get the context that the user is actually describing or the person who wrote it. But then the inverse of that was the second project where basically being able to detect tables really well is all I really need to do. Now that we didn't need annotation. I mean, I guess you could actually. The human in the loop piece is more to improve how the assignment engine works, right? So that's where sometimes, different ways to display even financial line items can be written in different manners. And then the human either has to verify that you fuzzy joined it correctly, basically, or you maybe completely didn't have it, and they reassign it and then they save it. In both cases, they go back to their own dictionary to sort of improve on the process. But the problem is the downside of it, some folks don't like that, right? They assume that, like, if I'm going to throw it to a vendor, I want everything to be magical and it just works. Which you could do, but then you require the whole corpus under NDA and then build your own sort of training set and go through a public. So this was designed in a way that you can throw almost any type of financial document to it, except for the public ones. Because the public ones, they're dense, they're like noisy, they're not really, not noisy, but they don't move the needle for my differentiation issue. I sell that anyway through basically other channels, right? Through feeds, basically. So, but yeah, like that's one of the battles with that app is mostly explaining to the customer and even our salespeople sometimes like where the balance between how much of a human in the loop is required, and there's no such thing as basically a silver bullet all the time. Yeah.
And can you just give an idea of what the team size was? Like how many people were involved in each of those case studies?
Yeah. So I mean, I would say about 20 people, like generally between tech and data science, right? So that's about that. Thank you very much.